The Foundations of Geometry by David Hilbert.
Chapter 6, Pascal's Theorem. Section 32, the commutative law of multiplication for an Archimedean number system.
The demonstration of theorems 36 and 37 rests essentially upon certain mutual relations concerning the laws of operation and the fundamental propositions of arithmetic, a knowledge of which is of itself of interest. We shall state the two following theorems. Theorem 38. For an Archimedean number system, the commutative law of multiplication is a necessary consequence of the remaining laws of operation. That is to say, if a number system possesses the properties 1 through 11, 13 through 17, given in section 13, it follows necessarily that this system satisfies also formula 12. Proof. Let us observe, first of all, that if A is an arbitrary number of the system, and if n is equal to 1 plus 1 plus ... plus 1 is a positive integral rational number, then for n and a, the commutative law of multiplication always holds. In fact, we have a times n is equal to a times the quantity 1 plus 1 plus ... plus 1, equal to a times 1 plus a times 1 plus ... plus a times 1, which is equal to a plus plus ... plus a. And likewise, n times a is equal to the quantity 1 plus 1 plus ... plus 1 times a, equal to 1 times a plus 1 times a plus ... plus 1 times a, equal to a plus plus ... plus a. Suppose now, in contradiction to our hypothesis, a and b to be numbers of this system for which the commutative law of multiplication does not hold. It is then at once evident that we may make the assumption that we have a greater than 0, b greater than 0, ab minus ba greater than 0. By virtue of condition 6 of section 13, there exists a number c greater than 0, such that the quantity a plus b plus 1 times c is equal to ab minus ba. Finally, we select a number d satisfying simultaneously the inequalities d is greater than 0, d is less than 1, d is less than c, and denote by m and n two such integral rational numbers greater than or equal to 0 that we have respectively md less than a less than equal to the quantity m plus 1 times d, and n times d less than b less than equal to the quantity n plus 1 times d, then the existence of the numbers m and n is an immediate consequence of the theorem of Archimedes. Theorem 17, section 13. Recalling now the remark made at the beginning of this proof, we have by the multiplication of the last inequalities ab less than or equal to mnd squared plus the quantity m plus n plus 1 times d squared. ba is greater than mnd squared, and hence by subtraction ab minus ba is less than or equal to the quantity m plus n plus 1 times d squared. We have, however, md is less than a, nd is less than b, and d is less than 1, and consequently the quantity m plus n plus 1 times d is less than a plus b plus 1, i.e. ab minus ba is less than the quantity a plus b plus 1 times d, or since d is less than c, we have ab minus ba less than the quantity a plus b plus 1 times c. This inequality stands in contradiction to the definition of the number c, and hence the validity of Theorem 38 follows.
The Foundations of Geometry by David Hilbert. The material contained in the following translation was given in substance by Professor Hilbert as a course of lectures on Euclidean geometry at the University of Göttingen during the winter semester of 1898 and 1899. It was translated by E. J. Townsend, Ph.D., University of Illinois. The text was downloaded from Project Gutenberg with the following notice: this ebook is for the use of anyone, anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. Read by Jim Renholt. Programming and illustrations by Jim Renholt. 2019. Portrait of David Hilbert by Rita Ray Renholt. Thank you for listening.